we're going to do 8, which is viewing transient stability results. Actually, we did a lot of this already, so it'll go pretty quickly. The idea is we're going to talk a little bit more about plotting, but not too much. The results display, time values, events, and plot interaction. Most of the plot stuff we've already covered, so we'll zip through that pretty quick. This is after transient stability runs, you can see the plots, and we've gone through that before. There's also gobs of results if you save it in RAM. We talked about how to do that. A little bit on min-max values. We'll talk about that. Looking at the events log is quite useful. A lot of times you can do a simulation and some automatic event occurs, like maybe a limit was exceeded and something tripped, and that will help explain why you're getting the behavior you got. A nice thing about all this is it uses the PowerWorld standard case information displays so that you can easily copy it into Excel or paste it or send it, do whatever you want on it. Let's go ahead and open up the TS9 bus fault no plot case. Everybody got that open? And then go to the transient stability analysis form and do a run. So just open, add-ons, transient stability. This is already set up. It does a fault at bus 5, and then it self-clears the fault after 0.1 seconds. So just go ahead and run it so we get some results to look at. And it should run. Okay. Then we'll go to the results from Rampage. This gives you a lot of results, and we'll go through the different types of results that are available here. Okay, so everybody should be on the results from Rampage. The first page on this is the time values. On the time values, you get to see anything that you saved or data that you defined a plot for. So this is all available, and it saves them based on whatever frequency you specified for saving the results. So we talked about that last time. You do it every time step, which we did here, every third, every fourth, whatever you want. A nice feature on this is, particularly in large cases, you can either group the fields shown here using this column order field, which is right there. You can either show object, then field, or field, then object. So the objects on this one would be the generator. So do you want to see all the fields for generator 1, then all the fields for generator 2, then do the object, then field? If you switch it around, it will show the field then object. So in this case, you would get all the megawatt fields, all the megavar fields, all the bus volt fields, so on and so forth. We also allow you to filter what fields you actually want to see. So this is something that I use quite a bit because I'll be doing a run and maybe I want to just look at speed on the generators. So I will, over here, it says choose fields to display. What I'll typically do is it starts out all checked. I'll do the uncheck all. If you do uncheck all, that gets rid of all of them. And then let's say we just want to see the generator speed, then you see the generator speed. So it provides you with a way to kind of customize what you want to see real quickly. All the data is there, you're just not seeing it. Another way to filter is to use the area zone filters, which is right here. Area zone filters just let you see the fields for a particular area or set of areas. So I think in this case we only have one area. But if you go to case information up here on the top, case information, You're just looking at the general case. Then you see the area zone filters there. If you click on that, you can see what areas you're set to display. It doesn't have an impact on this one because this just has one area associated with it. But on large case, if you just want to see the BPA footprint, then you just check the yes for BPA. Okay, we show time values for just about everything you could want: bus, load, switch shunts, branches, DC lines, so on and so forth. They're all specified under results options. Okay, so are there any questions about the time values?
So with this is a lot of detailed information. I really like it. If I want to trace a block diagram, a complex block diagram, understand the calculation behind it, if I go through these things, it should give me enough things to validate it, right?
Yes. But usually you would not be storing that data. So let me just give you an example of this. And this would be something that most people don't want to do. This would be more the interested user who's saying, hey, why am I getting strange results for this particular model? But since you asked the question, and I do this all the time, I'll go ahead and do it. So what you would need to do is to go up to result storage, and if you go to the generator and you go over to the far side on the display here, you can save the states on the machine, the exciter, the governor, what have you, okay? Those are not checked by default, and they're not checked when you do save all because most people really do not care. But people like me, I care. Sounds like you care. So let's say we care. So let's go ahead and click those for the machine, for the 3 machines, and we'll do the exciters here. So we're going to save the states now for the machine and the exciters. So I just went over here, save states for the machine, save states for the exciter. There's other ones for governors and stabilizers. We don't have any of those in this model, so we're not going to save them. So then there's a couple other model types that you can save the states for. We don't want to save all of them usually because most people don't care, and we're wasting space and we're wasting time storing stuff. If nobody cares about it, let's not store it.
So all they're left with is save all. This check yes, that does not save all of these. There's a group that it saves.
Right. We use all in sort of all the ones that are not the ones we don't want to have you save. Yeah. Yeah, because we debated that, should we have them saving the states? Because a lot of people just go in and say, I want to save everything. And then it's a question, because sometimes, like on a stabilizer, you can get 20 states associated with that stabilizer. That's going to make the file bigger. Do you really want to see all those states? Chances are not. Usually you only want to see them on a particular model for a particular reason. So that's why we didn't put them in Save All. Okay, but in this case, we want to look at them. So once you've clicked that, go ahead and do Run Transient Stability. And then if you go to Results from RAM, and you look at the generator, now on our generators, we're just seeing the speed on the generator because we had just checked the speed box here. Let's say you're wondering, hey, why is my exciter behaving the way it's behaving? You can either check all of them to see all of them, but let's just check the states of the exciter. So you can uncheck the speed and just look at the states of the exciter, or you can leave speed checked and just scroll over. But let's say I want to check the states on the exciter. I guess I unchecked speed. I want to look at the states on the exciter. That provides me all the states on the exciter. Okay, so usually you wouldn't do this unless you've got a block diagram in front of you, or you just like to memorize block diagrams that helps you understand what the states are. I don't have that here, but we can go and look at the block diagram for one of the exciters. So let's go over here, bus 2. If you right-click on bus 2, you go to the generator information dialog. And if you go to the stability tab, we've been there before. Here's our exciter. Show block diagram. So you go to the generator dialog for bus 1, which you can get to from the one line, or you can get to it from a case information display. Go to stability. I went down to machine models, exciters, and these are all the parameters that were inputted to the model. Show block diagram. We'll show you the block diagram. I guess I have to zoom in. Okay, so this is a zoomed view on that block diagram. Let's say you're really wondering what's going on with the voltage regulator, VR. So VR is it's the voltage regulator, and it's got an R max and R min, and you might want to know, is it hitting its maximum? Is that what's going on? So I'm going to close this because I can't have everything open, but you might have that printed out in front of you, and you would see this block diagram, and you know it can hit an upper limit and a lower limit. So let's see how VR behaves. And you can go in. I'm going to close that, close this, and that's the bug that we have to fix associated with the...
Are any of you getting an access violation when you do that?
Sometimes I do.
Are you on Windows 8 or Windows?
We have Windows 7.
Okay. But not everybody, just kind of sporadic. Okay.
So I went back now to transient stability application, and we're going to look at the results. We're looking at the states of the exciter. We were on generator 2, and this is bus 2, and this is the states of the exciter, and I scrolled over and I found VR. We're showing it by field, then object. Probably for this you'd want to switch it back to object then field, so you can do that if you want or not. If you do object then field, you got to scroll over to to generator 2, generator bus 2, find the VR column, and there it is. What I tend to do is I'm sort of lazy. I just do the quick plot. So I'm going to look at this column. So I'm looking at the VR value for exciter 2, something that only the interested would do. And I would right-click on that column and go up to plot column, and I would get a quick plot of that response. So there I'm seeing the response on VR. Maybe this means something to you. You know, you can see when the fault is applied, it spikes up, it gets up to 3. So let's say you want to just have it spike up to 2.5. So what I'm going to do is I'm going to go back to the generator dialog. So I move this over, and I go back to the one-line diagram, look at the generator information dialog, go to stability, exciters. Here are the parameters. The IEEE T1 VR max is set to 3. Let's just set that to 2 just for fun. So we just change that and set it to 2, save it, hit OK to close that, and then go back to transient stability and rerun it. So I go back to transient stability, I rerun it, my results are right there. I scroll over to get to generator 2 again, and I look at VR, plot the column, and now I'm hitting that limit. Okay, so you can get a lot of detail very quickly.
So you're rerunning it and it's overriding previous data. What if you had extended or shortened your time from 10 seconds to 5 seconds? Would the old data from 5 to 10 seconds stay there, or does that automatically disappear?
It should all go away.
It should all go away, but let's just check that to make sure. So Gordon wants to be convinced that it goes away, so we're going to change the end time from 10 seconds to 5 seconds. Change that to 5 seconds, then do run transient stability, then go down to the results from generator, and then plot it, and there you go.
So the main purpose of clear all time values in memory is more for, well, why did that get in there?
Oh, that was more for memory problems, or memory, because that's there, it's mostly if you're using the loaded in from hard drive option to view the data, and then you want to get rid of it.
Let me also comment on something on results. Let's say you've done this wonderful run and you think, I want to save this. I want to keep these results around. On a 9-bus case, it runs really fast, so it doesn't take a lot of time. But on, a WCC case, you spent time doing the simulation. You want to store the results so you can show them to people or do whatever, and you've saved them in RAM. Under the result storage, the store RAM options, so if we just go there, result storage, this says store results to RAM, so under result storage, every time step we had that checked, save the results stored to RAM in the PWB file. If you check that, it'll store all your results in the PWB file. Why you might not want to check that is you can have a lot of results and you can have a gigantic PWB file. Okay, maybe you want that, maybe you don't. I mean, sometimes I do it. I've got one that I'm going to use for frequency analysis later on today that I did store some of the results to RAM and saved them in the PWB file, so I've got them so that you can see them. Let me show you something else that is useful if you want to go through a simulation and see the gory details.
Sounds good.
Oh, yeah, John?
Yeah, quick question now. Prior to the setup, or prior to running the simulation, do you have to specify which of these various states of quantity needs to be saved, or would that just be...
You either get all the states for an exciter or none of them.
Did you have to specify that before the run or after?
Yeah, you have to specify it before the run. Anything with saving, we're not going to save it unless you tell us to save it. So after the run has gone through, it's not saved. However, I'm going to show you how you can see all the states when the run is going on right now without having to save them.
Maybe I'm confused, but it should initialize to 0, right?
No. The derivative of the state should initialize to 0.
Right.
The states themselves, let me go to the block diagram here. Oh, not repeating the question. Okay. The question was, should the states initialize to 0? And I said, no, the state shouldn't initialize to 0. The state should initialize to whatever value, but usually their derivative, practically always their derivative is going to be equal to 0. So if we go, this is the IEEE T1 block diagram, and I'll show you how the states get set. They're labeled here with the little colored circles to say what their numbers are. When we initialize on an exciter, the key field that an exciter puts out is the field voltage. That field voltage is determined from the machine model that we figured that out by saying, okay, for this machine model, what is the initial megawatt, megavar, and terminal voltage on that machine model? That comes from the power flow. Okay, so you change the reactive power output of that generator, it's going to change the E field. We calculate that when we initialize transient stability. In this model, it can either be multiplied by the speed or not. That's the per unit speed. That would usually initialize to 1. This field value, this field value becomes the state variable associated with this integrator block. So this might be 2.6. Its input in steady state, since it's an integrator, the only way it's going to be in steady state is if its input is equal to 0. So that state will be equal to 2 point whatever I said. Its input will be equal to 0. So when we go to, this leads into where I was going. If we go back to, I need to fix that, but if we go back to the transient stability display, and we're going to go to states manual control, which we talked about briefly yesterday. So let's go there, and we'll look at the initialization, states manual control. This has a button called Reset to Start Time. When you click Run Transient Stability automatically, it resets it to start time and it starts. This allows you to kind of do that manually. If you're having an issue with a case, you can kind of see all the gory details. So you should be clicking on Reset to Start Time. This lists all the states in the case. And in a WCC case, there might be 100,000. You can sort it and move through it pretty quickly. All these bind options and stuff like that work. Usually I just find if I want to find a particular state, I can scroll through this case info display really fast, even on a WCC model. This is a small case, so you might want to know what is the initial value of the E field for generator at bus 2. The initial value of the E field is 1.7893. This column lists the states. This column here lists their derivatives. So this is the derivative, and those should initialize to 0. So when you initialize a large case, oftentimes I will sort this derivative field to make sure that it's all 0. And if it's not 0, I will look to say, why is it not 0? One reason why it might not be 0 is because you're initializing with a value outside of a limit, and you told us not to change the limit. So let's say you want to look at what's the response on this system as we're running it. So this one doesn't do anything till time t equals 1. So let's do what we did yesterday. Run until a specified time. Set that equal to 1 here. And then do run until a specified time. That runs the simulation up to a specified time. Things turn yellow here because they're indicating that what you're looking at is a pause simulation. This pause simulation is transferred over to the power flow side, and we talked about that yesterday. Let's do one time step to move forward. This has a time step of a 50th of a second. So I clicked do a specified time step, so I'm now at 1.02 seconds. Alternatively, I could have put in 1.02 there, but that's too much to type, so I usually put in 1 and then I click that and go forward. So now we're paused at 1.02 when that fault is on. So if I move this out of the way, this is our fault on system. Okay, and it's actually visualizing. This was set up, the blue arrows are visualizing reactive power flow. The faults, I think it's at bus 5, right? I mean, it looks like all the reactive power is going into bus 5. The fault's on at that bus. Okay, but you want to know what are the states doing. So you just have to open up the generator dialog. for whatever generator you want to look at. You can do that from a one-line diagram. You can go up to the case information display, look at the generators, and right-click on it that way. Or you can use one of the transient stability displays to get to it. Since I've been right-clicking on the one line, I'll go another way, which is the case info display. The case info display up here shows the network. Usually that shows data for the power flow, but at this point in time, it is showing data associated with our transient stability run paused at this time. So I'm listing all my generator records there. This is what it's doing at time t equals 1.02. Okay, now usually you're not going to do this, but we wanted to give people easy access if they wanted to see it. And I know a lot of you just want to, run a transient stability run and just see is it stable or not, and Gordon's going to talk about that. But this is available if you want. So if I right-click on the one, I click on generator 2, right-click, do its show dialog. That's the generator information display, which we've been to a number of times. Go to stability. This is the input parameter display that we saw before, and in this one, it's because I didn't reset it, it's still changed to 2. Okay, that doesn't matter if you changed it or not. These tabs here show all the input data. We have another tab that is only populated when you're paused in a simulation, and that's called terminal and state. If you click on that, it gives you a lot of details about that generator at this point in time. And it's telling you the terminal values, what's the mechanical power input, what's the accelerating megawatts, terminal megawatts, megavars, internal delta, frequency deviation, field voltage, field current, quadrature, direct axis value. This is associated with the terminals. If you want to get into the machine states, this has a GenSal model. This tells you the 5 state values and their derivatives. If you go over to the exciter, that tells you the 4 exciter states and their derivatives. Some of them are ignored. In this case, VT is the sensed field, or the sensed terminal voltage. It has a time constant of 0, so that means, just like we talked about yesterday, you're assuming it's so fast that it's algebraic, so there is no derivative, it's ignored. And what we see here, the sense voltage, is the same as the actual voltage. But you get all this details. On some models, we toss in other fields that we think might be useful to people, like we're showing you the saturation value. More details than most people would ever want to know. But if you want to know them, the idea is to get them easily accessible. Okay, so let's say you've seen all the details you want to see. We're paused at 1.02. You want to finish up, so go back to the transient stability form and just continue. Okay.
The phone has something similar to a spread value. When I'm looking at the table, and I just want to quickly see what has the biggest change. What model has the biggest change for you?
That's the min-max.
Yeah, let's this is the min-max, but there's also something that we're debating whether to put in or not. So let's continue this to finish the run. So we finish the run, and I'll get to your question in just a second. I do want to point something out. If you're doing a run and you're on this all states display, I'm going to do the run again, and you'll notice that it's a little bit slower. Run transient stability. It's taken a while to solve this 9-bus case because the way the options are set up for this case, it's refreshing this as you go through, and that takes time. So you can, if you're running a WCC case and you're thinking, why is it taking so long? or longer than normal, it might be because you're sitting here on the all states display watching this display refresh, and we're having to refresh a display with 100,000 states in it because that's what you're asking us to do. But now we've done the run, and you want to know what are the spread on some of these values. So we're going to go back to results from RAM. We had talked about the time values, which gives you the individual details here. There's also the min-max values. If you go to the min-max values, which is the next one over, it shows you right now we've just put it for buses and generators. We could add loads in there. Probably should add loads in, we just haven't. We have defined certain values that we think people care about, and we store what the original value was, what the minimum value was, when the minimum value occurred, what the max value was, when it occurred. Okay. Now, there's only specified values that get stored, but we try to store the ones that people care the most about, which are bus values and generator values. What we don't have now, and what we have thought about doing, is doing this on the state variables. Because I think PSLF does do that on the state variables. And we've thought about doing that, but we don't know if people would really need it because we provide so much data available on the state variables. But we could add that in. It probably would be an option. And anytime you're doing a min-max, there is a little bit of, you have to store the value, and you also have to check it every time step to see if it's gone outside of the min and max. So there's a little bit of overhead associated with that. So there's a trade-off in this.
The more information, the better.
Well, yeah. I mean, we give you a lot of information, but you guys want to see min-max on state variables? Most people wouldn't, but yeah, I mean, I've thought about that because we, as I was saying last time, we've done a lot of validation on this, and I've gone through a lot of PSLF results, and you're looking at what they provide for results versus what PowerWorld provides for results, and PowerWorld provides all the states all the time, and they don't. So we're like trying to figure out what's going on based on what they provide, and on certain models, they provide certain values, but they're not all the states. So any of these that if you want to plot them in the plots display, Caroline talked about that. Let's say I want to quickly get a nifty plot that shows all my bus frequencies. Okay, so I go back to the time values. I'm like, oh, I wanted to make a plot of all my bus frequencies. Luckily, I stored them, but I didn't define a plot for them. Can I do that quickly? The answer is yes. So what you would do is click uncheck all and then click frequency. So we're just going to see the bus frequencies. And there's 9 of them. If we go and just select all 9 columns, and which one is that? Create plot definition. So I selected all 9 columns across here of the bus frequencies. Then I right-clicked on the display to get the local menu, and I select Create Plot Definition. If you select that, it automatically creates a plot definition for you and plots it out and shows you the results. You can then go in and modify that plot definition. And as I said last time, don't be shy in abusing the plots. Like I'll show you an example hopefully later on today, or maybe it'd be tomorrow, of how we're working on a case right now at University of Illinois where we're taking advantage of this to figure out what's going on in a larger case. It's a WCC case. But let's say I wanted to know, oh, what is that one that has the highest angle there? If you go and there you hover over it until it shows you something meaningful,
Need,
don't move.
more hover time. That's always a debate of how long to leave the hover, the pop-up there.
Yeah, so it gives you a lot of data. Talking about the states, let's go back to the states. And do you want to see min-max values on the states, or wouldn't you like to see a graph showing all the states really easily displayed? So if you're really interested in the states, rather than just showing you the min and max, because we saved them, I can go back to the results page. You go to the results from RAM generator. Now I'm going to go and uncheck all again and just check the states from the exciter, and I'm going to change it. Let's say I just want to see all the VR states. So I'm going to change it object then field. I'm going to flip that around, field then object. And, well, we'll just do the E field. Here I'm selecting the 3 E fields. So I changed this so I just want to see the states from the exciter. So I unchecked all, then I selected just show me the states from the exciter. Sorted it by field then object, so I'm getting state 1 from my exciter, state 2 from my exciter, state 3 from my 3 exciters. And then I do that, select the 3 columns, and I create the plot definition, and there's the graph of my 3 E field values. So rather than just seeing a min-max, now I get the full response on the ones that I care about. If you're following along at home, we're on slide 16 now. On slide 16, we're going to go back to the results from RAM tab, and we have looked at time values, min-max values. Now we're going to look at the summary one. So if you just click on summary, this gives you a summary of that solution, most of which will not be of interest to you. This is mostly timing statistics and a little bit of details on the solution itself. So you would seldom go here, except you might want to know how long did that solution take to solve. So that's the first value given here. The maximum angle difference really isn't that helpful usually, although if your system's going unstable, then that'll be a high value.
Point generators have capability curves embedded in the power flow. Are the limits in the capability curves mandated in the stability limits also?
No. The capability curves aren't associated with the model. Okay. I mean, that would be, I mean, what was used to define the capability curves was probably associated with the models that are defined in transient stability, but the reactive power limits aren't there.
Okay.
Yeah. They're more detailed exciter limits that would have an impact.
Okay.
Yeah. The next one over is events. This is a key one to look at. Events tells you what events occurred during the simulation, and the events include the events that you specified should occur, but they also include the events that might have been caused by a relay operating. And this can be crucial when you do a larger run and you might get strange behavior or something that looks unusual. Might be because you've got a relay that has a overexcitation limit value and you exceeded that value and you had it set to trip the machine. So you're like, how come I got that blip occurring at time 22 seconds? You go to the event list and it'll usually show at 22 seconds this occurred. So do you have examples of that?
Yeah, I can find examples. And,
yeah, okay.
And the way that I use the events is as a user, and I'm not digging into is the data correct or not. You know, I'm using it to find limits. And so if in fact that happens, and then I'm making the assumption that this is in a screen and that was an unstable condition, and so that now is going to be a candidate, that contingency is going to be a candidate for further investigation. I can have 200 contingencies with switching records, and maybe only 10 are interested. At least I've covered system-wide, what all of the simulations, for example, all the 500 kV lines, are there any problems, and maybe there's only 10 lines that have a problem to investigate, and even that might not be a problem. And then if it is in fact unstable, and a condition like that could show up in the event as under voltage, under frequency relays kicking in and dropping load, then that's an unstable condition, you're above the limit, if the data is correct.
There's a little bit of filtering options up here on the top, that if you unclick user, it gets rid of the user-defined events. So if you had a whole bunch of user-defined events and you wanted to get rid of them, just uncheck that. In this case, the only 2 events we had were user-defined. That's what you told it to do, so we don't have any other ones. And as it says, whether you check this or not, we record them all. We just give you some filtering options up here. Okay, the last page is the solution details. Don't go there unless you really care. It's solving network mismatch equations. Actually, we're doing 2 of them because we use the second-order Runge-Kutta method. Every time step, this gives you details about what's going on each one of those time steps. Very, very few people would care, but we care, so it's there. So the rest of this section from slide 19 to slide, the end of the way, slide 34, is more details about the plots. Caroline covered most of this. The key takeaway on the plots is if you care, play around. There's a lot of stuff there. If there's stuff that's not there, you can easily get the time domain data into Excel, and you have a ton of Excel stuff that you can use. But there's a lot of stuff in the plots, and very few people are going to be playing around with this, but there is stuff you can do. Okay, so if you want a nice, pretty plot for some reason, go for it. And a lot of people will set up a plot. So once you've got a setup that you like, you can save it in an aux file and use it elsewhere.
The plot definitions, you opened one up from...
Oh yeah, from an aux file.
Yeah.
Okay, anything else on this section?
Where can where is there to see the eigenvalues? Is it one of those values?
Coming up in section 11. We're going to talk about single machine infinite bus after Caroline does 2, then I'm back up on section 11, so we'll get to that. Anything else?